significant Reynold number of fluid flow. Introductions. Fluid mechanism is branch of physics concerned with the study of fluids, liquid and gases, and the forces acting upon them. Understanding fluid flow is crucial for designing systems in engineering, natural processes, and daily life. One of the fundamental aspects of fluid dynamics is determining the behavior of fluid flow under various conditions. The Reynolds number, named after Osborne Reynolds, is a critical parameter used to predict whether the flow will be smooth, laminar, chaotic, turbulent, or somewhere in between, transitional. The Reynolds number is dimensionless, making it a useful tool in various scientific and engineering applications. Basic of fluid flow. Fluid flow is a movement of fluid, liquid, or gas from one location to another due to a driving force such as pressure, gravity, or mechanical energy. There are different types of fluid flow which can be characterized by their velocity, direction, and behavior. We have laminar flow, we have turbulent flow, and transitional flow. Laminar flow fluid particles move in smooth parallel layers with little to no mixing between the layers. This type of flow occurs at lower velocities and it is typically for fluid with higher viscosity or in a small diameter pipes. Turbulent flow. In turbulent flow, fluid particles move chaotically with eddies, with swells, resulting in higher degree of mixing. This type of flow occurs at higher velocities and it is seen in layer pipes or with lower viscosity fluid. Transitional flow occur when the flow shifts from laminar to turbulent or vice versa. It is characterized by irregular fluctuation and the flow is not fully established in either from Reynolds number play key roles in predicting the transition. Understanding this different type of flow is essential for engineers because they significant affect this affect the design and efficiency of systems involving fluid transport, such as pipelines, systems, and event aircraft. Reynolds number definition. The Reynolds number is a dimensionless quantity used to predict the flow regimes of a fluid. It is defined as the ratio of inertial forces to viscous force in the fluid. Reynolds number is used to predict the transition between laminar and turbulent flow at low value of Reynolds numbers. The flow tends to be laminar, while at higher values, the flow becomes turbulent. The transition between the two occur around in a critical Reynolds number, typically around 2300 for flow in pipes. Dimensional analysis is a method used to understand the relationship between different physical quantities by identifying their fundamental dimensions, such as mass, length, time, and temperature. In the case of fluid dynamics, dimensional analysis helps to derive important parameters like Reynolds number. It involves using the dimension of variables involving to form a dimensionless quantity, which is useful for comparing different fluid flow situations regardless of the unit used. For example, when deriving the formula for Reynolds number, dimensional analysis show that the ratio of inertial forces, which depend on velocity and characteristic length, to viscous forces, which depend on viscosity, in the key to predicting flow behavior. The process of dimensional analysis simplifies complex fluid flow problems by reducing the number of variables involved and provide a clear understanding of the relationship between them. Types of flow: laminar, transitional, and turbulent. Understanding different types of flow is essential to comprehending the significance of the Reynolds number. The flow of fluid can be categorized into three main types. Laminar flow occur when fluid flow in parallel layers with minimal mixing between them. The flow is smooth and there is a little no disruption of the fluid layer. Laminar flow typically happens when the Reynolds number is less than approximately 2,300. This type of flow is common in small diameter pipe or with higher physicality fluid. Critical Reynolds number. The critical Reynolds number is threshold at which laminar flow transition to turbulent flow. It's generally considered to be around 2,300 for flow in pipes. However, this value can vary depending on the geometry of the system and the fluid properties. The value of Reynolds number of at which transition occur is influenced by factors such as pipe roughness, fluid viscosities. The Reynolds number play a crucial role in a wide variety of real-world applications. Below are some of the most common areas which is apply pipe and ducts in systems that transport fluid, such as pipeline and duct and plumbing. The Reynolds number helps engineer design systems to optimize flow by predicting whether the flow will be laminar or turbulent. Engineer can determine the required pressure, diameters, and material of pipe to minimize energy losses or avoid damage due to turbulence. For instance, turbulent flow pipe can cause frictional losses and wears, whereas laminar flow is more energy efficient but require careful control over flow velocity. Importance in engineering and design. The significance of Reynolds number in engineering and design is immense, particularly in fields that deal with the fluid mechanics. There are a few reasons why it is important. Optimizing energy efficiency by understanding the flow using Reynolds number. Engineer can design more energy efficient system, for example, in the fluid transportation system. Laminar flow minimizes energy losses, while turbulent flow is necessary in certain cases, such as in heat exchangers. By predicting the flow types, engineers can optimize pipe damage, materials, and flow rate to ensure energy is not wasted. Predicting flow behavior. Reynolds number allow engineers to predict flow behaviors in a wide range of applications, from design pumps and to study natural phenomena like ocean currents or atmospheric circulations. The ability to predict when flow will transition from laminar to turbulent help engineers anticipate and mitigate problems before they occur. Safety and reliability. Reliability in industry where fluid flow is critical, such as in the power plant or chemical processing. Maintaining predictable flow behavior is essential for safety and system reliability. For example, turbulent flow in a pipe might lead to vibration, pipe wears, or even catastrophic failure if not accounted for during the design phases. Reynolds number helps avoid such risks by providing a clear understanding for conditions. Flow continue in microfluidics. In the field of in the field of microfluidics, which deal with the behavior of the fluid in small-scale divers. The Reynolds number is used to control the flow of the fluid in channel on the microscale. At such small scales, laminar flow dominates, and engineers use Reynolds number calculation to design efficient microfluidics divers for applications like drug delivery, diagnosis, and chemical reaction. Simulations and visualization. In modern engineering, simulation and computer modeling play crucial roles in understanding fluid behavior and predicting Reynolds number values. Computational fluid dynamics (CFD) is a powerful tool used to simulate fluid flow in different systems from pipeline to aircraft. This simulation provides a visual representation of the flow, helping engineers and scientists analyze fluid patterns, predict transition between laminar and turbulent flow, and optimize system design. CFD simulation use Reynolds number as a key input parameter by inputting various fluid properties such as viscosity, density, and velocity. Into the simulation, engineer can visualize outflow behavior in different conditions. This visualize allow for identification of flow separation points, evaluation of turbulence intensity, optimization of design. In conclusion, the Reynold number is fundamental concept in the fluid dynamics that has a broad application in engineering, science, and medical field. By providing a dimensional ratio of inertial forces to viscosity forces, it allows engineers to predict the flow behaviors in systems involving fluid, whether in the design of pipeline, aircraft, aircraft wings, or medical device. Understanding the Reynold number helps optimize the flow for efficacy, safety, and performance. From Osborne Reynolds pioneering experiment in the 19th century to the modern day use of computational fluid dynamics, the Reynolds number has proven to be valuable tools for analyzing and designing fluid systems by accuracy, predicting whether flow will be laminar or turbulent. Engineer can prevent cut failure, enhance system performance, and improve energy efficacy. As technology continues to advance, the application of Reynolds number in emerging fields like microfluidics and environmental engineering will only grow. The ability to control and optimize fluid flow at both large and small scales is essential for tackling the challenge of the future, from suitable energy system to medical uh, innovations. In conclusion, the Reynolds number remains a key concept in a fluid dynamics, providing valuable insights that influence the design and the operation of the fluid-based system across multiple industries. Thank you.